Now we're going to look at the last of the three linked pathways that ends in the production of ATP. From all that work that's been done by glycolysis and the citric acid cycle with respect to producing ATP and transferring electrons to those electron carrier molecules. Again, we have a list of questions that you should be able to answer when you're done studying this topic. We'll look at where this process occurs. We are going to review reduction reactions. We'll take, after this introduction, we're going to do some problems together. We'll look at the organization of that transport chain. There are 4 complexes that we'll study in detail. We'll look at chemiosmotic coupling and how that protein gradient that is built up in the electron transport chain drives ATP synthesis. And there are a couple other questions here too. So, where does this occur? If you recall, the citric acid cycle enzymes, and we haven't covered this yet, but also the enzymes that catalyze fatty acid oxidation are located in the matrix of the mitochondria. So here's a figure or a cartoon drawing of a mitochondria. It has an inner membrane space, as you can see here. So this smooth outer membrane is the outer membrane. And then we have this convoluted inner membrane. And it is in the inner membrane that we're going to find the electron transport complexes embedded. So citric acid cycle enzymes are in the mitochondrial matrix. So this is a gel-like solution within that mitochondria. And interestingly, just a little FYI here, each eukaryotic cell has about 2,000 mitochondria, and these occupy about 1/5 of that total cell volume. So they take up quite a bit of space in a cell, and they're very important, obviously, due to their function. So we've seen this slide before, but now we're going to focus on the C portion of the slide. And this is the pathway through which electrons from reduced fuel molecules are transferred to molecular oxygen. Hydrogen ions are pumped into the inner membrane space in the mitochondria, and then the proton gradient is used to drive ATP synthesis. We're going to take a look at the important carrier molecules. We've seen them before in glycolysis and the citric acid cycle, but we're going to take a look at their structures now. FADH2 and NADH are in the reduced state when they carry electrons to the electron transport chain, where they transfer those electrons and then become oxidized. The electrons that are transferred participate in sequential oxidation reduction reactions in redox centers in the 4 enzyme complexes before they're finally reduced, or before they finally reduce molecular oxygen to water. During this transfer, protons are pumped across that into the inner membrane space, and it's this proton gradient that accumulates on this side of the inner membrane that is then utilized to provide the power to drive that ATP synthesis. So here is the structure of NAD. NAD plus, we don't show the positive sign here, but it is deprotonated. This is a derivative of nicotinic acid or vitamin B3. It's also related to a compound that we'll see in the pentose phosphate pathway, NADP. The difference is the NADP contains a phosphoryl group at C2 on the adenosine molecule. This is the reduction of the oxidized state of NAD. Here it is in its +1 state. When we it reacts with a hydrogen ion and picks up 2 electrons, it becomes reduced to NADH. And of course, this is a reversible reaction. FAD, or flavonine adenine dinucleotide, it has a riboflavin group, and this is from vitamin B2, and it also has a diphosphate group. FAD here is in its oxidized state. It can pick up 2 electrons, 2 protons to be reduced to FADH. Again, this is reversible as it is an electron carrier. Actually, this should be FADH2. Sorry, I just noticed the subscript is missing there. One other that we haven't seen today, flavin mononucleotide. This has a prosthetic group that resembles flavin adenine dinucleotide, or FAD, but it lacks that AMP group that FAD has. So it too is a 2 electron carrier. It can pick up 2 protons, 2 electrons, and be reduced to FMNH2. And finally, there's 2 other types of, well, this is a type of redox center. These are non-heme proteins. We have 2 types, but each consist of the same number of iron to sulfur ions, and both are coordinated with sulfur ions. So Fe then, in this particular one, is coordinated by 4 sulfur ions, and each of those 2 iron atoms, is coordinated by 2. Iron then can fluctuate between the +2 state and the +3 state. So it can accept or be reduced and then transfer those electrons. So before we start looking at the complexes in this transport chain, I want to review redox reactions. So we're going to take a look at the standard free energy, and we can calculate that by the negative number of moles of electrons that are transferred, multiplying the Faraday constant, which is 96,482 joules per volt mole, and delta E. So this is the change in the standard reduction potential. And we're going to do some problems that involve this equation. But before that, let's look at a standard reduction potential table. We can use these standard reduction potentials to predict directions of redox reactions. And I know that I'm having a hard time in my view right now reading these potentials, but I hope you can notice that they go from a positive here at the top to a negative here at the bottom. Okay. So, and we have as our, well, we don't have a standard here, and in typical standard reduction potential tables, we have hydrogen at 0. That's not shown here, but that's okay. So those at the bottom of this graph or this column are strong reducing agents and will be oxidized. The more positive the reduction potential, and that includes increasing or decreasing, I should say, decreasing negative values and then increasing positive values. The stronger the positive value, the stronger the oxidizer will be. So these are strong oxidizing agents and will be reduced. These are strong reducing agents, and will be oxidized. At this point, we're going to take a break and work some redox problems, and then we'll continue on by looking at the complexes in the electron transport chain.